You're listening to Innovators, the podcast from Harris Search Associates, where we speak with global leaders in education, research, engineering, and the health sciences, and ask them to share lessons learned as they continue to advance the frontiers of innovation and discovery. Today's podcast will be led by Rick Skinner, Senior Consultant.
The December 27, 2019 issue of the journal Nature is replete with research articles, news, and comments that suggest what's taking place now in the field of biomedical engineering could lead the casual observer to conclude that the field has moved now to a mature state of development, from which direct and indirect consequences are forthcoming. And if so, there is a host of ethical, social, policy, and protocol issues that will have to be considered. Our guest today on Innovators is Professor Ajit Yoganathan, who holds the Coulter Distinguished Chair in Biomedical Engineering at Georgia Tech. He was founder and is director of the Center for Innovative Cardiovascular Technologies. He is a fellow of the National Academy of Engineers, recipient of the Pilkington Award for contributions to biomedical engineering by the American Society of Engineering Education, and he chairs the subcommittee of the International Standards Organization Technical Committee. He holds numerous patents. Dr. Yoganathan co-founded the firm Apica Cardiovascular, which was situated in Galway, Ireland, with offices in Atlanta. The firm was purchased by Thoratec for $75 million in 2014. And as was noted in his biography, the impact of his contributions to clinicians is profound, especially in the area of congenital heart diseases. The surgical planning tool he envisioned together with Professor Jarek Rosenach, called SurGem, is one such practical application of fluid mechanics in treating infants born with half a heart, single ventricle so-called. This anomaly occurs in 2 in 1,000 of every child born in the United States and 4 in 1,000 in China. The Y-graft operation was listed as one of the top innovations in 2013 by the Children's Hospital of Atlanta, and has since been used in 50-plus children in Atlanta, the Children's Hospital of Philadelphia, and Stanford University Children's Hospital. Moreover, in what is surely an understatement, Dr. Yoganathan's bio reads, "It's worth noting that all prosthetic heart valves in use in the United States since 1975 have been evaluated in his lab either directly or indirectly. Additionally, he consults with major CV imaging companies such as Philips, GE, and Siemens." I think it unlikely we could have had with us a more knowledgeable figure on the state of affairs in biomedical engineering. So it's a pleasure to welcome Dr. Yoganathan to Innovators. I suggested the field of biomedical engineering is high on the curve of innovation diffusion, that it has an established body of knowledge about fluids and mechanics of living organisms, a growing repertoire of practical applications, and a maturing market for devices and procedures. Did I exaggerate the state of affairs in the field? Is it still in a pioneering stage, or is it a settled discipline?
Thank you, Rick, for the opportunity to be on this podcast. I take this opportunity in these trying times to address some of these issues and the role of the biomedical engineer that can help solve and resolve some of these problems. With respect to your question as to whether biomedical engineering is at a mature place, I would say no. Biomedical engineering has been around since the late 60s as an engineering discipline, but it started out mainly in the private universities such as Johns Hopkins, Duke, Tulane, Vanderbilt. Most of us who work in this field, who started in the 70s, came to the field from other engineering disciplines, such as mechanical engineering, chemical engineering, aerospace engineering, electrical engineering. We should keep in mind that biomedical engineering is interdisciplinary and multidisciplinary. That is very important. It pulls together engineers and scientists from different walks of life. Today, as we will see, the computer scientist plays a major role. And we have to keep in mind it is the term medical, meaning we have to work with our clinical colleagues and life scientists. I myself am trained with a bachelor's and Ph.D. in chemical engineering. I did my Ph.D. started in 1973 at the California Institute of Technology. But I would like to take a step back and talk about my journey in this field. I came in 73 to Caltech from London, where I just finished my undergraduate degree at the University of London. And I actually came to Caltech because of its small size and the warm weather. Caltech is a unique place where faculty do their own thing, well-funded, with high reputations. I came to work in the field of air pollution because that was an area that was growing at that time. However, when I heard faculty talk about their research, there was a faculty member, Bill Corcoran, who talked about blood flow and the noise blood flow created when the doctor took your blood pressure, the Krodkoff sound. And he was talking about how engineering comes to play in that space. I had never thought about this, even though I came from a family of doctors. Both my parents are doctors. My father was a private practice internist. My mother was an MD, PhD in pathology, professor of pathology in Sri Lanka. So to me, I never liked biology, so I was never going to be a doctor. I like math, I like chemistry, that's why I went to chemical engineering. So when Bill Corcoran talked about this, I decided to go talk to him. And he talked to me about using the stethoscope and looking at heart sounds to diagnose problems in the heart. So I always use a slide from Winnie the Pooh saying, how does one get into a field that you had no idea of getting into? And there's a very nice quote from Winnie the Pooh that he says, you keep looking for something, you never find it. Sometimes you fall into a hole, you were never expecting to be in the hole, and from there comes all sorts of opportunities. And that's how I got into the field of cardiovascular fluid mechanics.
A rather interesting hole to fall into.
Yes. So when I look back and I say, okay, so that's 1973, today is 2020. That's a long time for a field to have matured, but I would say no. Technology then was fairly nascent. Engineers were still trying to figure out what biomedical engineering was. And I think the field really took off in the mid-90s in terms of the educational efforts, with money from the Whittaker Foundation, as they looked to launch biomedical engineering departments. And it was then that major engineering schools, such as Georgia Tech, UC Berkeley, University of Michigan, MIT, Stanford, etc., the engineering powerhouses decided to get into this field. And when I say get into this field, was get into the area of undergraduate BS degrees, which is very important. I mean, there was research going on, obviously.
Right.
I came to Georgia Tech in 79. There were a couple of faculty at that time doing research in biomedical engineering, but there was no formalized departmental structure at Georgia Tech until 1997. And at that time, in the early 70s and 80s, biology was still in its nascent stage.
Exactly.
Biology was nowhere close to the level of physics and chemistry were in terms of science. The biological revolution started, I would say, in the mid to late 80s. And I think many people recognize the 21st century is being led by the biological revolution. And that is clearly going to also have a major impact on the field of biomedical engineering. Even in the area of medical devices that I work in, we're seeing a paradigm shift from doing, for example, implanting things in the heart with open heart surgery, which is what was the traditional way of replacing heart valves, putting bypass grafts and doing things by cutting open the chest, putting someone on the heart-lung machine and then doing the surgical procedures, to doing things now minimally invasively with catheters and while the patient is semi-conscious.
Mm-hmm.
And that technology today in the area of structural heart, which I work in, is really revolutionizing things. So when I look at it, technologies are evolving and we are on a steep slope. We are nowhere close to the top, and we definitely are not plateauing out.
Is it a convergence then of the growth of engineering unto itself? Because it was in the 80s that the engineering suddenly just began to grow rapidly. Secondly, the advances in biology. And then third, it sounds as though miniaturization and other aspects of technology also came together. Is that a fair statement, that that convergence of those three has sort of sparked this whole field?
Yes, I think that's correct. I think miniaturization, understanding more of the biology, the physiology, the anatomy, also imaging technologies, imaging tools.
Good point. Excellent point.
Minimally or non-invasive imaging, that's unlike putting a catheter, injecting dye, and looking on a scanner, radiographic scanner. But now we can use rapid CT,
That's right,
computer tomography, and we can also use non-ionizing radiation techniques such as ultrasound.
yes.
And these
So
are very,
MRI is still playing a role.
MRI is a very powerful tool. We use it significantly in our pediatric work because you do not like to expose babies and young children to ionizing radiation, because if they continue to have it, even though the dosages are very small, the cumulative effect is not good.
Very dangerous.
And MRI today gives us very good structural images, and also because of the physics of MRI, and the body is composed 90% of water, which is then protons, which the principle MRI works on, we can look at blood flow in 4 dimensions. In other words, 3 dimensions in space and 1 dimension in time.
Amazing.
And today we call it 4D MRI, where we can look at blood flowing in real time through the heart. And that gives us, as researchers, a very valuable tool, but also gives the clinician very useful information in relatively quick time.
So at this point, the early impetus has not abated at all. If anything, it appears to have accelerated, and the opportunity to explore whole new realms seem to present themselves. What you just pointed out with the fact that the body is mostly water and you do in protons, it's a perfect example. So far from being a mature field, it may actually be, I don't want to call it a juvenile, but maybe a teenager.
I would agree. It's more in the teenage years. I was thinking it's not nascent, it's not in its infancy, it's come a long way. We are today training real biomedical engineers, but these tools, technology has given us a lot more opportunities to understand some of the basic things that go on inside the human body.
That raises to me a question that while there was perhaps this convergence, the conditions must have been right to make the field emerge as powerfully as it has subsequently. I don't know all of those conditions. What were they? What made it possible for you and your colleagues to take advantage of that convergence and actually begin doing the research to build the field? Were there certain circumstances that made that better, more likely to occur?
I guess looking back, I think until the early 80s, NIH, which is the main source of biomedical funding, basic science, translational science, biomedical engineering, would only fund grants where the PI was normally an MD. MD. Yes. And even if there was a Ph.D. on the grant, there had better be an MD on the grant as well. My first few grants, I had to have MDs on the grant. Not that I didn't want to, but they had to be the major.
They had to be.
Yeah, right. That paradigm clearly began to change in the mid-80s. And today, many of us as engineers or basic scientists can get NIH grants. You don't need to have an MD on the grant
Mm-hmm.
if it's not necessary. But
Mm-hmm.
on my grants, we always have MDs because a lot of our work's very translational.
Well, yours is translational.
Yes. I think another fact that changed things was the Whittaker Foundation. The Whittaker Foundation
Mm-hmm.
started giving small grants early on. I was one of the first to get a grant outside the state of Pennsylvania.
Mm-hmm.
I got one in 1983. It was $35,000 a year for 3 years, so 105.
Mm-hmm.
But there was no overhead. It went a long way, and it started my launch into the pediatric cardiac area. But the Whittaker Foundation then it used until the late 80s, did what they call young investigator grants. So you had to be just in your early career or early career grants. And I think it got a number of us going. But then in the late 80s, they started what they called Whittaker Development Awards. And Georgia Tech was one of the first places to get a development award. Actually, we got it in 91, and it allowed us to hire new faculty in disciplines of mechanical engineering, chemical engineering, electrical engineering. Georgia Tech at that time did not have a department of biomedical engineering, did not give degrees in biomedical engineering, but that incentivized us to start an interdisciplinary Ph.D. program in what we call bioengineering. And I was the architect of that program. It was run through the College of Engineering, but it also had participation of the new College of Computing that had been created by President Creasine, who had just come in the late 80s. But it was an interdisciplinary degree run by faculty from mechanical engineering, chemical engineering, aerospace, and electrical engineering.
Excuse me, but you were able at that point to launch that program in large part because there was a body of research that had been done that made it feasible. On the other hand, the choice of bioengineering, was that a very self-conscious choice?
I think it was, because at that time we felt that the field, and as it turned out, it was a good choice because there was biochemical engineering going on activities, and we felt that that was better. We didn't, I think, consciously use the word medical because we really didn't have a medical school with us.
So you didn't have, so you really couldn't do that.
Right. I guess if you look at Hopkins and Duke, they all had medical schools. And Hopkins, the biomedical engineering department, actually is situated in the School of Medicine. It's in the School of Medicine, not in the College School of Engineering. So, but it was a degree that a master's and PhD degree were approved by the Board of Regents, and that got us started. And then these sets of development awards helped a number of schools. After that, in the late 90s, the Whittaker Foundation had decided that it was going to close its doors over a period of 10 years, 15 years, and decided to launch these leadership awards. Those were significant pots of money, and the criteria that they held as part of these awards was that you had to have a department. You had to have a department of bioengineering, biomedical engineering, call it what you may, but you had to have, and you had the coin of the realm had to be the undergraduate degree.
Now that fascinates me. They started with the insistence of an undergraduate degree.
Well, I think if a department is going to survive, going to stay a long time, you got to have undergraduate degree.
How did you recruit the faculty that I'm curious about that because you didn't have degrees in biomedical engineering. How did you recruit faculty, given the fact that you really those programs didn't exist? How did you recruit at those times?
So most of our faculty that were part of the bioengineering program, the faculty who had degrees in mechanical engineering, aerospace, chemical, electrical, the people, but were working in the space of biomedical engineering, bioengineering. That was their research areas. That was what their main focus was. And those were the people that helped launch the program. And then over the years, the last 20 years, obviously there have been people who have come out with biomedical engineering undergraduate and PhD degrees. But I would say even today, still a significant number of our faculty at Georgia Tech and Emory in biomedical engineering have degrees that are not in biomedical.
Would I be right to conclude that between NIH and the Whittaker Foundation, there was sufficient leadership as well as resources to get the programs launched? Are those the critical actors in this?
Yes, and I think another thing that should be remembered is the creation of the National Institute of Biomedical Imaging.
That's right.
NIBIB. Yeah, it's National Institute of Biomedical Imaging and Bioengineering. Actually, that was the last bill that President Clinton signed in early 2001.
My goodness.
Before he stepped down.
My goodness.
And that was quite a struggle to get that institute. And it took the radiologists, who are the imaging people, and other imaging folks, and the engineers battling traditional concepts at NIH to say there has to be this institute. And I think that also was a point of recognizing that biomedical engineering is a discipline here.
So it's possible in a period of about 20-something years, thereabouts, for 3 entities and some leadership within those entities to actually launch the entire field, to get it started in a very real way. And it's striking how pivotal a role Whittaker Foundation played. That's really quite remarkable.
I think it really did. I mean, I think hopefully history will continue to remember that, even though that foundation now is sunset and gone.
Sure. But I do think that it says to us something about the ability to overcome the lethargy that sometimes sets in, that kind of refuses to see innovation, especially when it has something to do with academic disciplines. It's tough to fight those battles sometimes. And I think in many cases, in the absence of something like a Whittaker Foundation who's able to leverage resources, it may not happen at all. It may not come about.
You're right. You do. And as you know, you've been in academia, you know it. People live in silos and everyone wants to guard.
Oh no, shocking statement by you, shocking statement.
Guard their sandboxes. And I don't think biomedical engineering can survive in a sandbox. It is not. It is something that needs engineers and computer scientists with different strengths coming together. You can call them biomedical engineers. They could be mechanical engineers. They could be people doing big data analysis today to work with the clinicians.
Various times in our talk so far, we mentioned the lack of a department or the lack of this. Let's talk about what is a somewhat unusual situation that you have. Georgia Tech did not have a medical school, still doesn't have a medical school. Emory University, while everybody knows it's a very fine, great university, it doesn't have engineering. And if it were, I don't know if it would be completely fair to say, but they're very strong in the social sciences and the humanities, for example. And yet, the two of you came together to create this new department of biomedical engineering.
It is a very interesting partnership, relationship that started, I would say, even before I came to Georgia Tech in '79.
Really?
So there had been overtures starting in the mid-'70s when Georgia Tech decided to go beyond its undergraduate mission. When Joe Pettit came as president, he was dean at Stanford. He's the one who came to Georgia Tech and said, Georgia Tech is now going to try to become a research university.
Major research university.
Major research university. And its academic units would participate in research. So there had been back and forth between Emory and Georgia Tech. I've been told that each one had made overtures to the other. It was like a dating game that never took place. But in 1985, Georgia Tech was celebrating its centennial. And as part of that, there was obviously a big fundraising campaign. Pete Pettit, one of our alumni, gave $1 million or $1.5 million to create a chair in engineering and medicine. He used the Stanford model of collaboration with medical school and engineering school in the Bay Area, he said. And he said he would like to see something like that. He was a Georgia Tech graduate.
He was an alum.
He had lost a child to SIDS. That's what, when he went and created the company called Healthdyne. That's what created his wealth, and he gave back. So as part of that, Georgia Tech really started looking at the opportunities of what, here we are now getting a chair. We don't have a department. There was only maybe half a dozen faculty. I was one of them. And as part of that exercise, also at the same time at a cocktail party that Christmas of '85, Executive Vice President for Research at Georgia Tech at that time, I think it was called Vice President for Research, Tom Stelson.
Yes.
Tom Stelson was quite a gambler. When I started, if you brought $1 in, he was willing to give you $2. So he, at a Christmas party, he and Charlie Hatcher, who was a cardiac surgeon, head of cardiac surgery, drive a red Ferrari or one of those sports cars. And he was, in addition to being a cardiac surgeon, he was the vice president of the medical enterprise. What we now call
Emory Health,
which is now huge. But and supposedly over a cocktail, these two guys chatted, and each said, "Okay, if you put in $200,000, I will put in $200,000 to start a seed fund." And out of that was born what was called the Emory Georgia Tech Biomedical Technology Center. Those words were very carefully chosen, alphabetically, Emory Georgia Tech Biomedical Technology Center. And the idea of the $400,000 was to seed research between a faculty member at Emory School of Medicine, a faculty member in the technology space at Georgia Tech, which was obviously dominated by engineering, and computer science was fairly nascent. And that was the requirement. You had to bring two of us together. $30,000, roughly a grant, would support a graduate student on each side, $15,000 at that time stipend, or half a postdoc with supply.
Right.
That program took off like a rocket, because there's nothing like money to get people to the table. The overhead that came from grants, from the seed grants, because after 2 years, you had to go out, external funding, NIH, NSF, NASA, whatever, was horrendous. So the program paid for itself many times over. And I ran that program from '92 until about 2000, when the program ended, 2002. The initial director of that program, there were co-directors, one from Georgia Tech and one from medical school. That was the beginning of the partnership between Georgia Tech and Emory. We had also looked at the Harvard MIT model of the HST program, and we found many issues that we did not, it was not the pathway. We said, if we could get research growing, education will follow. And in '96, Mike Johns, who was the dean of the medical school at Hopkins, came to take the position that Charlie Hatcher had. Yeah, so as the executive vice president for medical affairs. Mike Johns, after a few months in Atlanta after the Olympics in '96, that was the time of the Olympics in Atlanta, after the summer, approached Mike Thomas, who was our provost, and he said, "Hey, are you willing to create a department? I'm willing to put in X number of positions if you will put 2X on a model of X to 2X. He actually volunteered 6, and he asked Georgia Tech whether they would put in 12. And that was the start. And Mike Johns, having been dean of medicine at Hopkins, and the medical school, the biomedical engineering department, which was then the #1 department.
#1.
And still is #1, and we at #2 are trying to topple them. Knew the value of engineering. He also knew that Don was coming to the end of his 5-year term. He had the opportunity to renewing it. And maybe this was an opportunity to bring Don Giddens back here if we create a department, and that's what The department, there was a joint faculty committee that was put together in the early in 1997 of faculty from Georgia Tech and Emory, recommended the creation of the department. But they also made two other critical recommendations that I think really show how this thing worked. A, they said, start out with a joint PhD degree, start with that. Solidify your partnership on this seed grant research program that has been so successful. Bring together that with the students, with the joint degree. And two, out of the 18 faculty positions, no more than 3 of those could go to existing faculty. In other words, you had to hire
new blood.
Yes. And this was done on purpose because we did not want the other departments to feel that we were cannibalizing their thing. And this would be also the only way to grow the program.
Precisely.
With a bolus of 15 new faculty lines. And we said, if we could have filled those 15 with existing faculty, but that wouldn't have got us to it. So that was, I think, and I think Wayne Clough was instrumental in that. He had the vision together with Mike Thomas, who was the provost at the time. And then Don Giddens was the founding chair. I was the second faculty member to move into that department because I was running the bioengineering PhD program. I was asked to create this joint PhD now. And there were 3 other faculty that came in with one-third appointments. So we had the 3, the rest were all hired from the outside.
So in the space of a relatively short period of time, you created a new critical mass.
Yes. I think the other thing that needs to be kept, you've been in academia, you know how things evolve. It takes years and years. The Board of Trustees at Emory approved this joint department so the faculty committee met during the spring of 97. Emory Board of Trustees approved it in August of 97. The September meeting, the Board of Regents of the University System of Georgia approved it.
That's unheard of. That's unheard of.
Never heard. Also keeping in mind, Emory is private.
Private? You're a public institution.
Yes. Emory is heavily endowed by Coca-Cola money. Georgia Tech is a state university. And I think the reason that both the Board of Regents and Board of Trustees saw this as a unique opportunity was the fact that they were not scavenging from either.
Exactly.
As you mentioned, Emory does not have engineering. Georgia Tech does not have medicine. It makes a perfect marriage. Now you could say, why doesn't Georgia Tech partner with the Medical College of Georgia, but it's 120 miles away. And here was an opportunity with, in reality, a top class medical school.
I'm not going to ask you to comment on this. I'll just make a statement. It sounds to me like the stars aligned remarkably well. Those sorts of moments in history don't happen very often, especially in academia, where there's always someone who's going to be critical of what's happening. And as you say, whenever resources are being thrown around, it does become a very volatile issue. So it just strikes me that, again, a precise moment in time came. It was seized upon by a group of leaders in the board, the 2 boards, because to do that meant that they had to have complete confidence that this investment was going to work. I must say, I don't know whether it's one of those things that lightning strikes and it makes it happen, and then you have to go out and look for more lightning strikes. But that's a remarkable set of circumstances to lead to the kinds of collaboration that you have with Emory. That's a remarkable set of circumstances. And I'm not sure how often that would come. I just can't imagine it.
No, I agree with you. There are things lined up, and that obviously a lot. But there's also leadership. I
think a lot of life is living with compromises you don't want to make anyway. In this case, nobody had to compromise. People were able
nobody had to compromise. Also, the economics in the state of Georgia were good.
Really quite good at the time.
Very good, actually, at that time.
Yep.
And we were also just We had created the Institute for Bioengineering and Bioscience
Mm-hmm.
under Wayne Clough's leadership, and a new building was coming online.
Yep.
So everything was lining up. And then so to create a new department was sort of the icing on the cake at that time.
I'm going to completely change ground on you. In the little time we have left, I know your field is fluid. I understand that your interest is in hearts and so forth. But right now, this country is facing something that is unprecedented. There's nothing any of us can look to say, well, at least it'll be like this. There's nothing that we can grab hold of. At the same time, some of the advances in biomedical engineering have been so astonishing and so rapid that there's probably somewhere somebody thinking that biomedical engineering is going to pull a rabbit out of a hat. Is that possible? Is that where biomedical engineering is, that it literally could reach into a hat and pull out a rabbit, in this case being a vaccine?
I think biomedical engineering can clearly be a catalyst for that. It still needs the basic scientists, people doing genomics, people who understand viruses, bacteria, looking at all these epidemiologists, etc. But I think engineering and biomedical engineering can and will play a major role in handling this virus and hopefully squashing it.
Let me interrupt very quickly to ask, could this have happened 30 years ago?
No, I think 30 years ago we could, no. There are a number of biomedical engineers who are working in vaccine development.
Exactly.
There's this area called immunoengineering, that's where the antiviral.
Mm-hmm.
But I think we ought to also remember, as I was watching on TV on 60 Minutes on Sunday, within 2 weeks, Chinese scientists had put this ABCD of this virus. They had isolated it, and it's all the letters, yes. Now all you had to do was import that into a computer program, and I'm now talking in very lay term, to come up with what should be the vaccine. After getting the code, this company out in Massachusetts came up with, here's the solution for this problem. The computer said, this is what you need. Okay, it took 3 days for the computer program. All of that comes from engineering, big data, everything comes to play. However, we now need to create this vaccine or the antiviral therapies. And that takes time. And that, again, engineering play a role. However, at the very end of the day, whatever we create in the laboratory, whatever we create on a computer, you have to test it on a human being. And that takes time. You got to make sure whether it's a vaccine or antiviral therapy is safe and it's efficacious. And that's where the role of the FDA come in. That's why we need to have clinical trials. And I would like to go back and make a comment that Bill George, former CEO of Medtronic, once said when he had a heart valve that failed, and we did some work to tell him why it failed, because all the bench studies and all the animal studies said this new heart valve will do wonders for patients. And he said, I spent millions of dollars buying this valve from another company, but what we forgot, or we should remember, is that the human body is the most complex bioreactor that is out there. So we can test these vaccines in rabbits or mice. The proof of the pudding is you have to do it in human beings.
I want to close today and invoke something personal. I grew up in Savannah, Georgia. I was the son of a paper mill worker. And I can remember as a young man coming to Atlanta on a train and going over to what was then Georgia Tech, just a couple of buildings over on 10th Street and so forth. I want to thank you for what you've done. You've stayed at Georgia Tech now throughout most of your career, and you've made some extraordinary contributions. And so as a native of the state, I want to thank you very, very much for the work you've done, for the work you'll continue to do. And I want to thank you for being on Innovators today.
Thank you very much.
Thank you for listening to Innovators, a production of Harris Search Associates. We'll have more insightful conversations with global thought leaders to follow.